So hopefully quiz 3 went all right, and today we are taking our journey more on persistence and talking about something more modern. So we'll be talking about SSDs and RAID. So solid-state devices, most people probably may have not even seen a hard drive before. They're the more modern way to do storage, but they have their own little quirks that make it difficult to program for, and the transition was kind of odd. So they use transistors like RAM to store data rather than magnetic disks. So they don't have a problem where you can take a magnet and actually, corrupt them. So they have no moving physical parts or physical limitations. They have higher throughput. They have good random access, unlike what we saw before with hard disk drives that really, really want sequential access. And if you have random access, the performance gets like orders of magnitude worse. They're more energy efficient, better space density, but their cons is they're going to be more expensive. They have lower endurance. So with SSDs and other flash devices, there's actually a limited number of times you can write to them before they wear out, and then they can no longer hold a charge anymore and you can't use them. So if you want to optimize for SSDs, one thing you need to do is minimize the number of writes you can if you want, because that is kind of the limiting factor with how long it actually lasts. And it's going to be more complicated to write drivers for, and that comes as a result of just how it's constructed, and we'll see what that looks like. So if you rip open an SSD and look at the kind of the package, this is what it looks like. So we can ignore like the dye in the yellow and the plain in the brown. And for programming wise, we only have to care about blocks and pages. Thankfully, the pages in the green, they're typically 4 kilobytes, so they're the same page size as we already use with virtual memory. And then the blocks, all you need to know about the blocks is that they contain multiple pages, and we'll see why we actually have to care about a block containing multiple pages in the next few slides. But just to give you an estimation of like typical speeds, them being much, much faster. So pages, again, typically 4 kilobytes. Reading a page for hard drives, things were on the order of milliseconds. So for SSDs, they're on the order of microseconds. So reading a page is 100 or like 10 microseconds. Writing a page is like 100 microseconds. And then erasing a block, which is why we actually care about the layout of it, is 1 millisecond. And why do we care about erasing a block? Well, that's the only way to erase data on an SSD. You can't erase individual pages. You have to erase blocks at a time, which is the complexity with writing drivers for this. So you have to understand that and do some things so you know that, hey, this whole block is fine. Or if you have to modify data, if you have to modify one page, well, you're going to have to move it all to a new block and just write the other pages there that aren't modified. And then you can delete the whole block, and then you have to kind of update all the references. So you can only erase in blocks. So, and the other rules too are you can only read complete pages and write to freshly erased pages. So in order to write to a page, it would have to been erased. So you can't overwrite a page or do anything without doing an erase in between, which if you're writing a driver for this or you're trying to use it, is kind of annoying. So erasing is only done at a block level, and a block will typically have like 128 or 256 pages. And again, remember that the entire block needs to be erased before you can write, and then you can only write once to that page. So don't ask me exactly why that is. That is just how the hardware is designed. And then writing also in general is slow, because in the general sense, while you might have to create a new block or freshly erase a block, or possibly just copy everything else that you want from an old block over to a new block, and that's going to be much, much, much slower than with just a normal hard drive where you can just kind of read and write at will and you don't have to care about the actual structure of the disk or where the sectors actually are or anything like that. So SSDs need the kernel or the operating system's help to speed up access. So SSDs actually have some type of garbage collection on them. So they want to move any pages that are still alive to a new block, and there may be some overhead, so it kind of defragments itself a little bit behind the scenes. So it'll try and move blocks to freshly allocated blocks and try and kind of remove all the fragmentations and try and fit everything on a block instead of being spread out over multiple blocks. So if you are the kernel and you have access to disk controller, you might not even know what blocks are still alive. The SSD might think the disk is full when a file could be deleted, and that means not erased. So to delete a file, you can just remove all the references to it. You don't actually have to erase this or erase the block. You can just kind of let it sit there and then let the hardware go ahead and figure out, you know, hopefully I stop using all the pages on a block, and then eventually that block could be erased. So there's a lot of bookkeeping here associated with it, especially when the hardware might only care about blocks and not about the pages used on the block. So this is kind of like a weird type of fragmentation where you might have some pages available on a block, but the disk might not know that they're available or not, and therefore can't really do anything about it. So like with typical deletion, you just delete a reference to it, but the device might not know, hey, does this page on a block, is it actually represent a deleted file, or can it still access it? It would have no way of knowing. So there's something called a trim command that informs the SSD if a block is unused, because otherwise it will not be able to figure it out just based on the pages. Yeah.
So suppose like I download a huge game, 100 gigabytes, and I want to delete it, and I just like right click it and say like delete this file, and it just disappears from my computer. Is that means like it actually erasing everything in my drives, or just like say okay, you can just like write anything over it?
Yeah, so the question is, if I download a big 10 gigabyte game and I delete it, does it actually get erased on your SSD? And the answer to that is probably no, because it would be somewhat slow. So it would mark all those pages as being deleted, and then if it has this like trim command thing, it could tell the SSD that, hey, these blocks are no longer used, and then it's free to erase the blocks in the background, but it typically does that on its own time and not like when it's just idle, not doing anything else, because otherwise that information's there. And this is why you can actually recover some data, or if you delete files, someone that is really, really good at data recovery can still recover it, because it just kind of deletes references to it and doesn't delete the data. So this is kind of how data recovery works as well. So even though the operating system's not pointing at stuff, if you know the format of stuff, you can point at things and kind of probe around and see all your files that were deleted. So all the stuff that you think you may have deleted might not actually be deleted. And like an explicit version of this is like on Windows, your recycling bin, or Mac, and your trash. That basically keeps one reference alive to that file, so it doesn't actually get deleted on disk. And then when you clear your trash bin, it'll just remove that one reference to the file, and then it may actually be deleted on hardware, or it may not be. But that's also why recovering a file in trash is really, really fast, because it just recreates the reference that points to that in whatever the original location is you deleted it. And we'll see more of that when we get to file systems. But yeah, so trim, you might see this is more of a big deal when SSDs were new, but that's just the way of the operating system informing the SSD that, hey, this block's unused, you can actually erase it. Yeah, so far we've been talking about single devices, so now we can get into more exotic things. So sometimes just a single device is kind of jokingly called a single large expensive disk. So if you need more storage, one thing you can do is just buy a single bigger hard drive and fit everything on that. But people, it's kind of a mocking term because it doesn't sound good. It sounds like it's kind of mocking you because it's just one single point of failure. So one thing you will typically see, especially that you can also do yourself if you really, really care about your data, is something called a RAID, or a redundant array of independent disks, which just means it's just a bunch of disks that are linked together in some way to either improve its reliability or improve its performance over a single disk. So instead of just having a single disk with all your data can now be distributed across multiple disks, and there's different ways to accomplish this. So you can use redundancy to prevent data loss, so your data is in more than one place, or you could use redundancy to increase throughput. So if you have 2 copies of a file and they're both on a single disk, well, I can go ahead and read half of it from one disk and half of it from the other disk, and I can kind of double my performance, or at least for reading. So the first thing you might encounter, has anyone ever heard of RAID before? Okay, so some people have. So when you actually start caring about your data and like doing stuff, you might actually use one of these things. So they're actually good to know what they are. So RAID 0 is also called a stripe volume, and this is purely for performance. So data stripes will typically be in like size of 128 or 256 kilobytes and distributed over the disk. So those are like the size of chunks that are per disk. So if you had a big file that was in 8 of those chunks, then what RAID 0 would do is essentially put all the even number chunks on one disk and all of the odd number chunks on the other disk. So this way, your read and write performance is both doubled. So if I'm writing out all 8 chunks, I can send 4 of them to one drive, 4 of them to the other drive, so I'd have double my read performance, or write performance. If I want to read that A file, well, to read them, I read 4 chunks from one drive and then 4 chunks from another drive, so I would double my read performance as well. And this can scale up to as many disks as you would like. So you could do this with 3 disks, 4 disks, 5 disks, however many you have. So this is going to be like faster parallel access. Both read and writes are essentially going to be n times faster, where n is the number of disks. But now, instead of before when we had a single large disk, we had a single point of failure. Well, now we have multiple points of failure. So if we had our 8 chunks of our file here, well, if we lost one of those drives, doesn't matter which one, we'd lose half our file and it'd no longer be accessible. So if it was a video, it would just be corrupted. Anything would just be corrupted. It's just missing half its data, which would get worse if that thing was distributed over 4 disks. So any disk that goes down, that file is now corrupt and you can't read it because now you're missing data. All right, any questions about RAID 0? It's typically only used for performance. You're essentially trading off performance for more points of failure. So RAID 1, if you get into data hoarding or you actually care about your data, is kind of the cheapest way to go and most simple. So it kind of, you can think of it as creating a backup for you automatically. So it will just take 2 disks and make them an exact copy of each other. So if that A file is now 4 chunks, well, the exact same 4 chunks would be on the first drive as the second drive. So now we'd get double our read performance in this case, but for writing, it's just going to be as slow as a single disk because we have to write that data to both disks. But this will make it anything, any file you change, any file you create, anytime you save, well, the data is going to be on both disks. So now if one disk dies, well, you don't lose anything because the other disk is an exact copy of it and it's maintained like that. So you don't have to worry about that as much. But of course, if both disks die, then you lose your data. So it's pretty simple, but could be wasteful when we compare other techniques. So in this, every disk has a mirrored copy of all the data, and again, like RAID 0, this can scale up. So I could have RAID 1 for multiple disks. So I could have it for, you could have 4 disks like that they're all copies of each other. Your read performance will be 4 times as good, but your write performance is going to be the same as a single disk. But the only benefit is now to lose your data, you actually can lose up to 3 of your 4 disks. As long as one survives, you're good. You still have your data left. So it's got good reliability. Again, like if one disk remains, you still have your data. And good read performance, but there's a really high cost for redundancy. So everything is an exact copy. So we can actually do better than this, which we'll see next. And again, the con is the write performance, because we have to write all the data to all the disks. So the first one that introduces some type of parity, and what parity is just a little bit of information that can be used to reconstruct other bits of information. So the data stripes would be distributed over disk, or over the disk, and there would be one disk that's dedicated for parity. And the simplest parity scheme is just the parity bit is an XOR of all the other bits on the other drives, so that if one dies, it can be reconstructed. And what that would look like is essentially, well, for every byte of information, or every bit of information, so you'd have all your bits here. And then we could have, disk 1, 2, 3, and then our parity disk. Well, if these are all of our bits that are distributed, so say we have 1, 1, 0, 0, 1, 0, 1, 1, 1. So the parity is just going to be a calculation for across all of our disks. So the parity for the bit 7 on all of our disks is essentially the XOR of everything, which essentially just means, hey, the XOR, you can think of it, it means it's a 1 if the result of adding them all together is even, and it's a 0 if adding all of them together is odd. Or sorry, it's a 1 if all of them together are odd, and a 0 if all of them together are even. So here, our parity would be, 0. For the next case, there is an odd number of bits, so our parity would be 1. And for the last one, there's also an odd number of bits, so our parity would be 1. And the idea behind that is if we lose one of these disks, so let's lose the first row and just remember it was 1, 0, 1. Well, if we just lose that and we have no idea what it is, well, we can use that parity bit to reconstruct what that value was. So on disk 2, it's a 1, and disk 3, it's a 0. And then if I compute the parity across all the disks, including all disk 1, it's supposed to be even. So if I know adding all of them together is even and the last 2 disks remaining are odd, that means it has to be a 1 that I lost. So this is what you would do to recover your data. So if I lost disk 1, well, I look at my parity bit and what bits are remaining, and then I reconstruct disk 1. Yeah.
If we lose 2 disks, though, is it all over?
Yeah. So in this case, if we lose 2 disks, it's all over. I essentially have, I just have 2 unknowns, and I can't do anything about that. So have we taken differential equations and done like the sets, 2 unknowns and all that, linear, whatever, all that stuff? So all that stuff is from linear equations, which we'll see well, we won't go into the details, but if you want to know the details of how to reconstruct it if you're missing 2 disks, well, you'd need linear algebra. But in this case, I could reconstruct, so the first one would be 1, And then I know for the other one, for bit 6, well, disk 1 is a 1, disk 3 is a 0. So those together are odd. And then the parity says the result of all of them is odd. So the one I'm missing just has to be a 0 because otherwise I would change the result. And same for the last one. So my 2 disks together are even, and I know with the parity it's odd. So that means my disk that I'm missing is a 1. So that is at the basics how the parity calculation works for one level of parity. So of course, if 2 disks fail, it's all over, but we can actually reconstruct the information if a single disk fails. So also the problem with this one too is there's going to be a very uneven wear, because no matter what, whatever modification you make, even if it's only to a single drive, well, every single modification is going to have to go through disk 3 that's holding all the parity information. So it's going to be very, very unevenly distributed, where disk 3 is going to get a very disproportionate amount of the load because it has to store all the parity across all the disks. So even if you change just one disk, you have to reconstruct the parity. So if I change like A in disk 0, B in disk 1, C in disk 2, well, each of those is just writing a single chunk to the disk, while the parity disk would have to write all 3 chunks that is a parity of all 3 of those. So it's going to have way more writes happening to it than the other disks. But that's just to illustrate what a parity drive could do and what parity information does. So with parity, you essentially lose a single drive to just parity calculations, and you need at least 3 drives for this to work. But for the Pro, well, you get n-1 times performance. So you basically just remove the parity disk because it's a bunch of overhead. So you can read across n-1 disks and write to the other disks, but you'd have a little bit more writing because every write has to go through the parity as well. But you can also replace a single filled disk and rebuild. And you also get most of the space of all those disks combined while having some benefit for performance and being able to tolerate at least one RAID failure. So write performance can suffer a bit too because every write, no matter what, has to go to that parity disk. So RAID 5 is essentially, RAID 4 is never ever used because of that issue. And RAID 5 is the same idea where there's a single parity disk, except the parity is distributed across all of the disks. So in this example, disk 0 has the parity calculation for D, disk 1 has it for C, disk 2 has it for B, and disk 3 has it for A. So it's more evenly distributed across all the disks, but otherwise performs exactly the same as RAID 4. Yeah. So the question is there RAID 2 and 3? Because we skipped the numbers. So there is RAID 2 and 3, but they're really, really weird. So we won't talk about them. So typically, we're just talking about the ones that are used are 0, 1, 5, then we'll see 6, and then a combination of 1 and 0. But yeah, RAID 2 and 3 were essentially mistakes. So this is what RAID 5 uses, and so it has all the same pros as RAID 4 in terms of space. All of our calculations are the same. The only difference is the write performance is improved, and because we no longer have the bottleneck of the single drive, everything is more evenly spread out between them. But with this too, you can only tolerate one drive failure. Because I remember in grad school, I had a RAID 5 and one of the disks failed. And I was like, oh yeah, no problem. I can rebuild it. I can save information. But I didn't act that fast. Typically, disks fail in pairs together or generally at the same time. So I lost another disk while it was going, and I lost I lost some stuff. Yeah.
Why do they fail?
So if you buy them at the same time, typically, if all the wear is about the same, they'll kind of wear out about the same. So if you buy them at the exact same time, which typically, if you really care, you shouldn't do, you should buy them from different batches or something, because you don't want them to both die at the same time if you're using this. Yeah, so if you do this, you should space out like what batch they come from. For performance reasons, they should be like the same performance and stuff, because you're going to be bottlenecked by the slowest one anyways. So they should all perform about the same, but if you really care, you want to buy them from different batches probably. So go to another store. Well, hopefully they came from different batches. Usually they say what batch they came from on them. But yeah, typically if one dies, the other one's going to die close together. So don't do what I did. If a drive dies, go out and replace it. Because otherwise you're going to have a bad time. But if you wanted to kind of live on the edge like I did and have a bit more redundancy, well, that's what RAID 6 is. So RAID 6 just adds another parity bit per stripe. So instead of just being one parity, so that the original parity would be P, which is like the XOR, there would be another parity which would be something like Q. And to understand how you calculate the Q parity bit such that it's different and not using just a plain XOR, that's where the scope of this course will end, and you can look at on your own if you're really interested in that. But that will also tie into kind of your linear equations courses and all of that. But for all we care about, RAID 6 can just recover from 2 simultaneous drive failures. But now, due to the extra parity, we have less available space. So essentially, we're going to have 2 disks used for parity. So the amount of space we have is essentially 2 disks smaller than if all of them were just like in RAID 0. And for this, you require at least 4 drives. And the write performance is also going to be a little bit slower than RAID 5 because there's going to be some extra parity calculation. And it's going to be a bit more complicated than just doing straight XOR. So there's also an option here to do something that's called a RAID 10, but a RAID 10 is just a RAID 1 plus a RAID 0. So a RAID 10 essentially is going to have different stripes across all the disks, and then you would have a mirrored copy of everything. So let's draw that out, what that looks like. So, whoops. So for a RAID 10, which is sometimes called a RAID 1 plus 0, well, you need at least 4 disks. So disk 0, disk 1. Oops. So you would have your data striped across 2 disks. So you'd have like A0, A1, A2. So like with our RAID 0 before, where we just have all the data just distributed across the disk, we would have all the data distributed across the disk on one side, and then the other, whoops. And then we would use the other disks as a RAID 1, which is a complete mirror of each other. So there's kind of 2 dimensions to this. So across the disks, they're exact copies of each other, but between all the disks, this way, they'd be RAID 0, where all the data is distributed across them. So typically you use something like this. So there's going to be exact copy, so you're going to lose half the data due to redundancy because we have a RAID 1 in the mix, but we're not going to have all the drawbacks of it because we do use striping between the disks as well. So in this case, the number of drive failures you can tolerate is kind of dependent. So there's like a minimum and a maximum. So in this scenario, well, let's do another few more disks. So say I just added, here, let me rename them. Oops. So in this case, that would be our RAID 0 across those 3 disks. And then we'd use another 3 disks to have an exact mirror of that RAID 0. So disk 3 would store A0 and A3 exactly like disk 0. So disk 3 would be a mirror of disk 3 or disk 0. Disk 4 would be a mirror of disk 1. So it would contain like the A1 chunk and A4 chunk. Then disk 5 would contain the A2 and A5 chunk because it would be a mirror of disk 5. So now, how many disks could we tolerate failures for? What was our minimum and maximum number of failures we could actually recover from? Yeah.
Minimum 2.
Yeah. So minimum is 2. And why is that? Well, I could get really unlucky. And so each of these disks on this side have 1 mirror. So say this disk fails. Well, I can get really unlucky. And if its mirror also fails, like this one, then A0 is gone, A3 is gone because its mirror is now gone. So if 2 things fail, well, then if the wrong 2 things fail, then we are screwed. But in this case, in another way, well, that's our unlucky case. Our lucky case is, well, say this one fails. So now we have 2 disk failures, and we're still okay because we have at least 1 copy of every single chunk. So we just lost our mirrored copy of A1, but that's okay because we still have an A1. And then now a 3rd disk failure could happen, and we could be okay as long as we're lucky. But if you assume things happen uniformly, randomly, we're not playing very good odds here. But we essentially have a 50-50 chance of completely failing or not. So if either disk 2 or disk 5 fails like this, then you're still fine because you have a redundant copy of we have at least 1 A2 left and 1 A5. But we were 50-50 there because if disk 3 dies, then we no longer have any A0s or A3s. And then if disk 1 died instead, well, we just lost that data as well. So this has like a minimum and a maximum. So you can, depending on your luck, your minimum's always going to be 2 because I could lose my mirror. But the more drives you add like this, the more probability you have that you might actually be okay to lose 2 because it might happen with another pair. So you just have other pairs. If you lose both in a pair, you lose data, but you can lose 1 in multiple pairs and still be okay. And another reason why some people prefer this setup too is if one disk drive dies and you have to recreate it, well, if you're recreating it from parity information, well, you're going to have to do some calculations. So you're going to have to do a lot of XOR operations, and it's going to take some time. So typically, rebuilding a disk, if it's several terabytes, will take on the order of days. So with this scheme, there's no recalculation or anything. If another drive dies, to reconstruct the new one, you just straight up copy the one that survives. So there's no calculation, there's no nothing. You just copy it as fast as it can go, and you can reconstruct it in a matter of hours instead of days, which is, a lot more palatable if you're, running some very important thing, or, especially if it takes days and you bought them together and they fail together. So in the process of reconstructing the data you lost, if you lose another drive, you might be screwed. So sometimes you want to do this as quick as possible. So any questions about RAID stuff? Okay, cool. So we saw some more topics. We saw SSDs and RAIDs. SSDs are more like RAM, except that they're accessed in pages, and they're organized in blocks. And they have some weird rules associated with them, where you can only write to a freshly erased page, and you can only write exactly once. And you can only erase data in blocks at a time. So because of this, SSDs need to work with the kernel to get the best performance, where you need something like trim to actually, which basically just informs the drive that, hey, this whole block isn't actually used, even though it looks to you like it might be used. And we saw RAID, or the redundant array of independent disks, to tolerate failures and improve performance using multiple disks. There's a lot of ways to arrange that, and a lot more exotic kind of file systems and solutions to that. But the major ones are RAID 0, 1, 5, 6, and then RAID 10, which, as we saw, is just a combination of RAID 1 and RAID 0. So with that, just remember, pulling for you, we're all in this together.